essentially 3 or 4 steps in the semi formal approach, all of which are fairly intuitive. So, let us take the first step. We said that we cannot think of a power spectral density in the usual sense for the random signal, because it exists forever, it has infinite energy and so on, it is a power signal. So, what do we do? What we can do is we can start with the finite length realization. That means, I may have 1000 observations or 500, 524, whatever. I have n observations of a single realization of the random signal, right. So, that is what I have with me, V 0 to V n minus 1. This is what I have in practice. Can I take the Fourier transform of this finite length realization that I have? I can, there is nothing stopping me, right, it does not violate any of the requirements. So, we can take the Fourier transform and denote that by V n of omega. We are switching to angular frequency now from cyclic, but we may go back to the cyclic frequency soon. So, V n of omega is simply, what is it? It is the DFT, we have already talked about DFT, right, V n of omega subscript n. So, you can take the DFT and arrive at V n of omega n, right, and I can construct an empirical power spectral density like the periodogram. If you recall, what is the definition of periodogram? Mod V n of omega n square, that subscript n indicates that I have used n, I have constructed an n point DFT from n observations. So, I take mod V n of omega n square and divide it by 2 pi n. I can call this as the empirical power spectral density for the finite length realization. Until now things are okay, but now if I want to connect this periodogram, which is giving me an empirical power spectral density, power per unit frequency, to the process itself. What is the difference between the process and what I have here? First of all, this is a finite length realization, this is not even a single realization in its entirety. Secondly, the process is a collection of realizations, right. So, to be able to jump to the property of the process from the periodogram, I need to take 2 steps, 2 further steps. One, which is to extend this realization to its infinite realization, this is just a finite length one. And secondly, then I have to look at all possible realizations. So, if this is coming from the ith realization, then this is the periodogram of the ith realization. Am I right? So, and in fact, for the finite length part. So, now first what we do is we ask what is the limit. You can actually do 2 things. You can ask, for example, limit and then take the expectation, or you can say no, let me look at all the finite length realizations and then let n go to infinity. So, you have to have some imagination, not too much. Your true process is a collection of infinitely long realizations, and what we have is just a finite length realization. So, somehow from this finite length I have to jump to the full process, and in doing so I must guarantee that this periodogram makes sense, right. Right now for the finite length realization, does the periodogram make any sense to us? It does, right, because it is just an empirical power spectral density. If I take the average of all such realizations, finite length realizations, let us say, would it still make sense? That would be the average power spectral density for all possible finite length realization. And now when I let n go to infinity, so here I have not taken the expectation, so let us put in the expectation here. So, that is the first modification. We say that now I compute the average spectral power spectral density, It is still empirical, because when I take DFT, it assumes the signal is periodic and so on. There is nothing like a power spectral density. You have to keep asking yourself why it is empirical power spectral density, because I have taken the DFT of this finite length realization, and DFT assumes the signal to be periodic. So, there is no notion of power spectral density at all. We have defined an empirical one, and this expectation, by taking the expectation, what am I doing? I am actually looking at average for the entire all possible finite length realizations, but still this is not we have not gone close to the process completely. We have, right. There is one more modification that I have to make, which is to let the length of the realization go to infinity. Then when I do that, I would have spanned the entire process. So, when I do this, that is, now we say limit, evaluate this in the limit as n goes to infinity. So, you see that is why it is a semi formal approach. We are only using some reasoning to take each step. Now, the question is, does this limit work out to something meaningful? Does it make sense to take the limit? Do you expect that this will give you something meaningful? What happens when you let n go to infinity? The frequency spacing now becomes a continuum, because until this point delta f was 1 over n, or delta omega was 2 pi over n. Now, when you let n go to infinity, the frequency spacing becomes a continuum, and as a result you throw away the subscript on omega and you replace it with simply omega itself. So, when you are looking at this, this is, you can say, some gamma of omega n, right, for the ith realization inside, and you can say that this is based on the finite length realization. But when you now do when you take the averaging and then evaluate in the limit, this now becomes a continuous function of omega. What do you expect this to tell you now, this gamma of omega? Look at the innermost one, right. This is telling us power per unit frequency. Now, this is for the expectation looks at all possible realizations, and then the limit allows you to stretch it to the infinitely long realization. So, what do you expect gamma of omega to tell you? We will ask whether this limit exists or not and so on, and we will come to that very quickly. But what do you expect gamma of omega to tell you? What about the process? What property is it revealing? Does it still have the flavor of a spectral density? And what is the interpretation of a spectral density? Here energy spectral density told us the contribution of a band of frequencies to the overall energy. We do not say of a single frequency, it is a density, correct. Likewise, you should expect gamma of omega to tell you what band of frequencies contribute to the overall power of the random signal, that is all. Can I ask this question? This is where some depth of thinking is required, and not too much it is not too difficult to imagine. I just now said gamma of omega can be thought of as it is a density function. So, if I were to integrate this gamma of omega over a band omega 1 to omega 2, what would this integral tell me? It would give me the contribution of the frequencies in that band to the power of the signal, of the random signal, right. But does it make sense to ask to make this statement, contribution of frequencies? Can we say that sinusoids and cosines are mixing up to produce V? Is it still legal to imagine that way or not? Can we imagine random signal being made up of sines and cosines? Yes or no? What do you think? The hint is something that we have discussed earlier. is it at least prima facie legal to think of a random signal being made up of sines and cosines? Yes or no? Then we should have been able to take a Fourier transform, right? But there was something else that we said when we were discussing Wiener's GHA. The mixing coefficient, the building blocks I can always think of sines and cosines. It is only the mixing coefficients now that are random variables. So, it is still okay to think of the random signal being made up of sines and cosines, but the coefficients can change with the realization. Think of it that way, right. That is the main difference, one main difference between the deterministic signal and the random signal world. The mixing coefficients are now random, you just have to keep telling yourself, although we do not deal with the mixing coefficients. And second difference is we look at all realizations collectively. We do not look at a single realization, we are taking expectation. When we define autocovariance, what did we do? We looked at the average property. When we look at mean, it is an average property. When we speak of variance, it is an average property. Always for a random process, it is about the average property, not of the specific realization, it is of the all averaged across all realizations. And that is exactly what is spectral density here too. The spectral density is also an averaged quantity, and the interpretation is that the area under the spectral density gives me the power, the contribution of the frequencies to the overall power of the signal, frequencies in that band. When we talk of random process, and ultimately if you are able to, one important takeaway from this course for you should be is, when you think of a random process, it should always be the collection of signals, not of a single signal. If you are able to bring yourself to that imagination, I think you have really understood at least one essential point of this course. Anyway, so this gamma of omega can be thought now as a spectral as a spectral density, but the question is, does this limit exist? How do I guarantee that this limit exists? You can't simply take limit of any function and assume it exists, correct? We have already learned that in math many times. So, that is the only thing that is remaining, at least in the semi formal approach, to establish the conditions under which I can think of this spectral density. So, how do we arrive at this condition? All you do is you start with the definition of DFT and plug in. So, what you do is you write mod Vn of omega n square, use your standard DFT definition, right. That is all I am doing on, I have done for you on the slide that you see right now. I have just taken the DFT, endpoint DFT, and mod Vn of omega square is the product of the DFT and its conjugate, for that is simple complex variable calculus. And what I have written here is rewritten gamma of omega in terms of, now do you see the autocovariance appearing? How did the autocovariance appear? First we wrote the mod Vn of omega square in terms of the DFTs, and when we do that and then take the expectations, that is where the autocovariance appears, right. That is why the semi formal approach is very nice. It straight away establishes a connection between the spectral density and the autocovariance function. And you can say some schools of thought use this approach to even arrive at the Wiener-Khinchin relation, and we will do that as well. But the point that you should appreciate is, through this semi formal approach, not only were we able to construct a spectral density function, not in a very rigorous way, but it is okay, and two, we are able to see now straight away the connection between the spectral density and the autocovariance function, okay. But the story is not complete yet. The story is why? Because we have not yet established the conditions under which we can have gamma of omega, but we are just a step away. So, you have this last equation on the screen, 1 over 2 pi limit n going to infinity, the summation f of L which is dependent on n times sigma L times e to the minus j omega L. So, from here we can derive the conditions under which the gamma of omega exists, and I have given the expression for f of L, it is 1 minus mod L by n. In fact, if you were to break up this into two summations, what would be the first summation? Remember, f is 1 minus mod L by n, correct? So, if you take the summation, forget about the limit and so on, if you just take the summation, you can write it as two terms. What would be the first one? That would be simply the dTft of the autocovariance, correct? And then you would have a second term. Somewhere, if you were to do the reverse engineering, which we are generally good at, you should expect the second term to vanish for in order to arrive at the Wiener-Khinchin relation, and that is exactly what it turns out. First of all, let me write those two terms and then we can straight away spell the conditions. So, I am ignoring the limit, you have L from minus n minus 1 to n minus 1. The first term is simply sigma of L e to the minus j omega L, and what about the second term? The second term would be mod L by n sigma L e to the minus j omega L. Clear? This is just plain algebra, there is nothing here. I have just taken the expression for f of L and then put it in there. Now, for the limit to exist, first of all, in the limit as n goes to infinity, both the summations should converge, correct? What is the first condition, what is the condition for the first summation to converge? What is the condition? Sigma is absolutely convergent, autocovariance is absolutely convergent, correct? And that is what we have assumed. And for the second one to converge, of course, you have 1 over n here in the limit as n goes to infinity. What should happen? So, if I take 1 over n here, remember that now there is a limit here as well. For this summation to converge, already we have required sigma L to decay. When we say sigma L should absolutely convergent, sigma L should decay, but we have not said anything about the decay rate, how fast it should decay. We will require further that it decays fast enough so that this entire limit exists, right? Because what is happening here, there is a mod L, although sigma decays, this can actually dominate if sigma does not decay fast enough, correct? So, what is required is that the autocovariance actually decays fast enough in the sense that it should decay faster than the rate at which L grows, that is all, right, because n has anyway fallen out of the summation. This summation should not blow up, and for that summation to not blow up, we require sigma to decay at a much faster rate than, or at a rate faster than the rate at which L grows. So, there are two requirements. One is that the autocovariance should be absolutely convergent, that is a must, which means that the autocovariance should decay. What does it mean? It means that I cannot think of a spectral density for any random process just like that. First of all, I can think of spectral density only for random processes that are not periodic. Secondly, it should be stationary, and that is anyway given. Among the stationary processes, I can think of spectral density only for those whose autocovariance is absolutely convergent, right? Are there stationary processes for which the autocovariance is not absolutely convergent? Yes, and those are your periodic random processes, okay. So, the summary is that the spectral density is now the Fourier transform of I am sorry, there is a 1 over 2 pi missing in the expression, I will correct that in the bottom summation, because if you recall there is a 1 over 2 pi right in front of the limit. So, your spectral density is 1 over 2 pi times the dTft of the autocovariance function, subject to the condition that the autocovariance function is absolutely convergent. Okay. Even if you do not understand any of this, as long as you remember the fact that the autocovariance function and spectral density form a Fourier pair, that is more than enough, which is what is the Wiener-Khinchin relation. So, we are stating things formally. We are saying that any stationary process which has an absolutely convergent ACVF can be now given a spectral representation. Why do not we call it as a Fourier representation? It is still based on Fourier transforms, right, I mean Fourier analysis. Typically, we talk of Fourier representations, of course, you can talk for any sequence, you can say it is a Fourier representation of the autocovariance sequence, but we use the term spectral to explicitly say that the Fourier transform of the autocovariance function yields a spectral density. When I take the Fourier transform of any signal, it is some quantity, it need not be the spectrum, but here specifically the Fourier transform of the autocovariance sequence is a spectral density function, and therefore, we call this as a spectral representation, right. So, if you remember that autocovariance function and the spectral density constitute a Fourier pair, that is more than enough, at least to compute and the spectral densities and so on. Now, using this Wiener-Khinchin relation, we can construct spectral densities for some well known processes. What I mean by well known is, what is the most well known frequently encountered stationary random process? The white noise, correct? The inevitable white noise process. Whether there is correlation or not in a process, definitely you have the white noise component sitting there. So, straight away using this relation, you can arrive at the spectral representation of white noise process. Simply apply the Wiener-Khinchin relation. Remember, we did not use Wiener-Khinchin relation to define the spectral density. We started with a fairly generic approach and then arrived at Wiener-Khinchin relation. Okay. And now the Wiener-Khinchin relation can be used to compute the spectral density. Think of it this way, until now we have described random processes in terms of autocovariances. Now we are describing the same processes in terms of the spectral density. That is the real nutshell, things in a nutshell for you. Straight away now you see, what you see here on the left is the theoretical expression for the spectral density. What is it that we have? We have gamma of omega for the spectral for the white noise as sigma square E over 2 pi. Remember, we are writing in terms of cyclic frequency. If the spectral density angular frequency, if the spectral density were to be expressed in cyclic frequency, you would only have sigma square E, but that is a minor point. The most important thing to observe is this is fixed for all omega. What is the interval for omega? Minus pi to pi, right. What does it mean? It means all frequencies are contributing uniformly to the power of the random process, right. Remember, I said something long ago when we talked of energy densities and power densities, energy and power. I said the energy or a power of a signal has to be related to the process that is generating the signal. So, if I say a signal has high power, it automatically implies that the process has that power to generate the signal. So, here what we are saying is all frequencies are uniformly contributing to the power of the process that is generating white noise. And in analogy with white light, which has uniform contribution from all frequencies, engineers call this as a white noise process. statisticians did not give that name. For the original name for this was the uncorrelated process, ideal uncorrelated process. But then engineers said, well, we will give it a name and call this as white noise, and it made sense because when you turn to AR and MA processes, for example, if you take an MA1 with some values for the coefficients, on you can get this autocovariance function, we are now very familiar with that, or I look at an AR1 with coefficient 0.5, we know the autocovariance function is given by this. When I look at the spectral density, what do you expect to see? Do you expect to see a flat one like this? No, right? What do you expect to see? What kind of spectral density do you expect to see for these processes like this MA1, AR1, whose autocovariance is not an impulse? It will be anything but not flat, correct? In fact, it turns out that they look like this. Of course, this is specific for this MA1 process. If the coefficient changes, or the sign of the coefficient is different, then you may get a different value, correct? But what you should understand is any deviation from whiteness, what does it cause to the spectral density? A non-flat one, correct? Which means, now what does it tell you about the process itself? When you look at the spectral density, what does it tell you about the process, nature of the process? Not all frequencies are contributing uniformly, they are not participating. Only a set of frequencies are participating in the generation of these processes. And once again, engineers call this as colored noise. Why? Because unlike white light, if I take a color red, green, blue, whatever color I take, we know from physics that the colors exist are associated only with a band of frequencies. So, they said all correlated processes are colored processes, whereas uncorrelated ones are white noise based on this spectral density description. So, when I tell you it is a colored process, you should understand it is a correlated process. Of course, further I may have to tell you whether it is MA1 or ARMA and so on, but the fact is any correlated process will have a spectral density that is different from flat spectral densities. There is a function in R, I will show you in the next class, ARMA spec. If you recall, we talked about ARMA ACF. What does ARMA ACF in R do? It gives you theoretical ACF. ARMA spec, go back, it is not in the stats package, it is in the TSA package. Try out ARMA spec, and of course, it is a good habit to develop the expression for the spectral density by hand and then use R to confirm that indeed you get that plot. So, now what we will leave with today's class is, on one hand you have the spectral density of the white noise process which looks flat, and on the other hand you have the spectral density of the correlated process which gives us a to paint the process, we say it is a colored process. When do you produce colored light from white light? How can you produce? Apply, right? People do that in many hotels and parties, they want to actually produce colored ones. Either you have white light and you apply a color paper, stick a color paper on top of the bulb, or within the bulb itself, I mean there is a mechanism of generating the colored light. Exactly the same interpretation now comes forth, what we have learnt, and we have come back in full circle to say that any correlated process, stationary correlated process that has absolutely convergent autocovariance, at least in this sense, can be given a filter representation, right. So, when I filter white noise, here I have written the signals, but behind the scenes what is happening? Filtering. So, the white light is actually passing through a color paper, and what kind of color paper is it? We do not know, it depends on the process, ultimately produces a spectral density that tells you what frequencies are present or contributing, let us say not present, contributing or participating in the generating process. So, when we meet again in the next class. What we will do is we will complete this discussion, we will also talk of the spectral factorization and then put a close to the spectral analysis. Okay? Yeah, hopefully you enjoyed the class.